Hi friends, in this series we will learn graph data science and graph machine learning using Neo4j. Today we look at centrality. Let's take the US airports as a graph network. So here we have 456 cities which have airports in USA, and then we have 70 plus thousand direct flights between these cities. So here we are visualizing just three cities: Albany, New York, Albany, Georgia, and Alamosa. Now we have a direct flight from Albany, New York to Albany, Georgia, and from Albany, Georgia back to Albany, New York. Whereas this Alamosa is not connected to any of these two cities. Okay, so let's visualize maybe few more. All right, so Alamosa, it is still not connected to any of these four cities, but as you can see, all these remaining four cities, they have a flight from each city to the remaining three cities. Here we have total 456 cities or airports. Now visualizing all of them, I can slow down the visual, but maybe let's look at one more example. So here we have 10 cities and we can see all the connections. So this time, as you can see, Alamosa, it is connected to this alliance. All right. So we will see how to load the data into the Neo4j graph database and then do the centrality analysis. So from this cities network, let's say we want to do some analysis or we want to ask questions, which are the airports which are more important and connected to other important cities within the network, or maybe which cities act as this transfer points or connecting hubs, right? For example, we might have many cities which does not have direct flight between them, but there are certain airports which act as transfer points or central hubs. So these are the sorts of analysis we can do using this graph centrality algorithms. We'll come to them in a moment again, but let's set up the graph database. All right. So we are going to use the graph data science as well as graph database libraries, just running locally. And then here we are creating graph data science client. Now let's read our dataset. So this version is dataset is hosted by this Stanford EDU. So here we have the nodes. Nodes are simply the cities, right? So here we have the node ID, and these are the city names, the population, latitude, and longitude. Okay. So here we have 456 cities. And then here we have the connectivity information. So using the node ID, we have the origin, destination. We are not going to use weight, but the total number of routes or direct flights is 71 plus 1000. Okay. Now, if there is a direct flight between every city to every other city, to and fro, we would have 200 plus 1000 direct flights, right? Because we have 456 cities. From every city, if there is a flight to every other city, that would be n times n minus 1, right? Because we are distinguishing the to and fro flights. We are not treating them as same. We are not dividing with 2. So we would have 200 plus 1000 direct flights. Whereas we have only 70,000 direct flights, which means there are a large number of cities which do not have direct flight to other cities. Okay. All right. So let's load the data into the database. So basically we have two data frames, one related to cities, the other one related to the connectivity. All right. So we use graph data science client. All we are doing here is So we are taking this nodes information, which is this, and we are creating nodes or the airport cities. So we create node using the cities, and we set the properties node ID, name, population. Okay. So from this data set, we just take node name and population. We create city as a node. Okay. And then the relationships. So this time we use the routes data, and we have a source and destination or origin and destination, right? So again, read this data. So here we are mapping the source node, the target node, and the relationship is has flight to. Okay. So we run this query. This will take some time. And here we are verifying that we have loaded the data correctly. Okay. So this time we are using the graph database driver. We are running this query, which is simply match all the nodes and return the count. Okay. And then we are printing the count. And here we are matching all the relationships and printing the count. So basically we are counting how many cities are there and how many direct flights are there, right? So 456 and 71,959, which matches exactly with what we have in our data. So the data is loaded correctly. All right. Now this data is in the database. Now to do the analysis quickly, we need to load the data into the memory, which is called projecting the graph into the yeah. All right. So here we are creating a projection. We give it a name airline, and what we want to project the cities and the relationships information. Okay. And this is stored in this variable G. The projection, the graph projection is stored in G. Okay. All right. Just printing some stuff. It took this many seconds. Again, the cities and the relationships. All right. The first algorithm we are interested in is called this Eigenvector centrality. Okay. Let me go back here. So Eigenvector centrality. What it does is it measures how important a node is within the network. Okay. When doing this, it consider other important nodes within the network. For example, we might have a node which is connected to many nodes, but a significant number of those nodes may not be important, right? Through this measure, we measure how important a node is in relation to other important nodes, right? The reason I am stressing this is, at a high level, these three algorithms are measured. They sound like same, but there are some nuances. Okay. So this one, it measures how important in relation to other important nodes. The other important is the keyword here. Okay. All right. So what do we do is, so from graphdatascience, the Neo4j library, it has already all the algorithms. We just simply call the algorithm with the data, right? So we are calling Eigenvector. Now there are different modes here. Mutate means write the results back to the graph projection. A couple of other options we have, like stream. Stream means it does not persist the result. It's directly print the results on the console. And then we also have write. Write means it write the results to the database. Okay. Notice the difference. We have the database and we have the projection. So the database is like any SQL database where we can persist the data. And then the projection is in memory for faster computations. Okay. So we provide our data or the network, and then we want to run this algorithm for a maximum of 100 steps. And when we mutate the results back to the projection, this is the name we want to give to this property, eigenvector centrality. Okay, so just run this algorithm, and then if this property is written because mutate, we can verify it. So you just ask the node properties. This time it should have eigencentrality. Okay, and here we are just checking if the algorithm has converged and how many steps it took. Yes, the algorithm indeed converged and it took 13 steps. So what this does is basically for every node in our network, it compute this eigenvector centrality and write the result back to the projection. Okay, and this is how the distribution is. Just the standard statistical thing like min, max, median, some percentiles, 90, 50 percentile, 99 percentile, 99 percentile, so on and so forth, right? But now let's write the result to the actual database so we can persist the results, right? So similar to mutate, here we are using write, we are writing the result back to the graph database. So it says 456 properties have been written. Now let's look at the top 20 cities which have the highest eigencentrality. Okay, so all we are doing is just map the cities, get the centrality and order in the descending order and limit to 20. It pretty much like a SQL query, right? Okay, so this is what we have. So these are the top 20 cities with highest eigencentrality. Okay, Los Angeles, San Francisco, Dallas, Las Vegas, so on and so forth. Okay, now let's look at betweenness centrality. Now, as I mentioned, these three metrics, they sound similar, but there are subtle nuances. Now, the betweenness centrality, it measures how important a node is as a connecting hub or transfer point within our network, right? As we saw, there are many cities which do not have direct flights. Now we want to find out the cities or the airports which act as these major transfer points or connecting hubs. Okay, that's what this betweenness centrality measures. Or in other words, it measures which cities have the shortest path between other cities which do not have a direct flight between them. Okay, all right. So the process is exactly the same. Instead of calling the eigenvector, this time we call the betweenness algorithm, right? So pretty much the same. Just call the graph datascience betweenness algorithm, input our graph network, again write the result as betweenness centrality. All right, again we look at the distribution, write the result to the database, and let's look at the top 20 cities with highest betweenness centrality. So this time here we have Los Angeles, Denver, New York, so on and so forth. Now, if you look at the top three here, Los Angeles, but these two are different, right? So Denver and network, they act as the major transfer points or the hubs. So there are many cities in USA which did not have direct flights. They transfer through Denver and New York. Okay, that's the difference between the eigenvector and the betweenness. Okay, and finally we look at the degree centrality, which is actually a very close to eigenness. Okay, all right. As I just mentioned, it's exactly the same. We just call the algorithm with our network and what a property we want to measure. The distribution, write it back to the database and look at the top 20 cities. Okay. All right. Let's go back to our three definitions. So I'll quickly revise. So the centrality, it measures how important or influence a node is in relation to other important nodes, okay, in the network. Now, nodes with high eigenvector centrality are likely to be major hubs or airports, but these are not for transfer, right? Or for connecting. They direct just have more direct flights between them. Okay. Whereas the centrality, it acts as these transfer points or connecting hubs. So this play a significant role in facilitating flow of air travel and vital for network connectivity. Okay. All right. And then finally, the degree centrality, it's as simple as counting which cities have the highest number of direct routes, right? It measures the number of connections or the edges a node in a network has. Okay, that's pretty much it. Thank you very much.